Hello everybody, welcome back to my channel. My name is Cha Cha, and today I'm going to be going over the fourth chapter of the Kaplan chemistry textbook for the MCAT, which is compounds and stoichiometry. Quick disclaimer that I like to say before all of my videos is that I am a student like you too who are studying for the MCAT, so I may make mistakes. If I do, please leave them in the comments and I'll make sure to address it because I am also studying um, for the test and I don't want to make any mistakes, and I'm sure everyone else doesn't want to either. Without further ado, let me scroll over and we can get this started. So first of all, before we kind of get into the nitty-gritty, it's important to talk about what some quick definitions. So what is a molecule? I'm sure if you've made it this far through your general chemistry classes, organic chemistry, biochemistry, anything that ends in tree, you have probably heard of what a molecule is, but you may not know the definition. So it's two or more atoms that are held together by covalent bonds. That is kind of a key thing here. Oh my gosh, if this will go. There we go. So ions aren't considered molecules. They're considered compounds, but not molecules. Compounds are kind of like an umbrella term, whereas molecule is a subcategory of that. Um, then we have formula unit, which is the simplest ratio or whole number of anionic compounds, and formula weight is the sum of atomic weights of individual atoms in the formula unit. Remember, whenever you see weight, kind of think like weighted average. So it's an AMU or grams over mole. Remember, 1 mole is equal to Avogadro's number, which is 6.022 times 10 to the 23 moles of X. And X can be anything. It could be eggs, it could be chlorine, it could be glucose, anything that your heart's desire, you could put it there. And X is more or less a placeholder. Um, yeah, then molar mass. So that's the number that you'll see if you're looking at a periodic table. You'll have your element, just number one, and then you'll have like um, a number down below that you'll be like, what's that? And that's your molar mass. So, in grams per mole. That's a number that you'll use a lot of the times, specifically in stoichiometry, like equations that we'll get to in a little bit. Um, Next I want to talk about equivalence. So it's kind of like how many moles of what we're interested in will 1 mole of the compound provide. So let's say that we're interested in protons. So for example, HCl will give 1 mole because there's one hydrogen atom in that molecule's makeup, I guess. H2SO4 will give 2 moles for every 1 mole of that molecule because or two equivalents, I guess, I should say, because H2 there's two hydrogens, right, in the compound. Whereas H3PO4 will give 3 moles of H hydrogen or proton because there's three. Gram equivalent weight is how much grams or how many grams is needed to react with that thing of interest. So you have molar mass over N, where N is the number of things of interest set. So for example, if we're going back to our proton examples, so HCl, it has 36.46. That is if you look it up in the periodic table, it'll have, that is what it will be listed under when you add hydrogen and chlorine up together um, over one because there is one of hydrogen or proton that we're interested in. So that's 36.46 grams. That's how many grams of that compound that you'll need in order to produce that like thing of interest. H2SO4, if you add up everything in that molecule, like all the hydrogen, sulfur, and oxygen, you'll get 98.08 grams per moles. So you divide it by 2 because we're interested in having 2 protons, and that'll give you 49.04. That's another thing that you'll need to react for that thing of interest to produce. An equivalent in a molecule, when it's unknown, but you have the molar mass and gram equivalent weight, you could use this equation. So the mass of the compound over the gram equivalent weight. Molarity, this is something that you'll see very often when you're talking about concentrations. It's the most thing. You also see molality, but that's more or less for like the temperature density changes. So like boiling point, elevation, and then like freezing point, like depression. Um, those are the only times you'll kind of see that instead of molarity. So it is moles of solute over liters of solution. Notice it's not solvent, it's solution, so it's in total. So you add up the solute and the solvent if it is a volume. It's when you care about the total compound, remember, not the individual components. So, 1 mole of HCl over 1 liter is 1 molarity unit, or 1 m. And over here, you have 1 mole of H2SO4 over 1 liter is equal to 1 unit of molarity, or 1 m. And as I said, it measures concentration. Whereas normality, this is when we care about equivalence. So that's when you're measuring the moles of things of interest, when you're measuring the concentration. So it's a subunit, not looking at the whole compound, unlike molarity. So you'll look at equivalents per liter. So equivalence is essentially saying how many of, like, when you're looking at 1 mole of that compound, how much of that compound of interest will that give you? So for HCl, because there's 1 hydrogen in that compound, it's 1N over 1 liter will give you one. Um, oh, 1N, just capitalized. And then for H2SO4, it's same thing. You have 2 hydrogens instead of that 1 hydrogen for HCl. So that's 2N over 1L. So that is a normality of 2N. Um, Basically, what this says too, if you're like trying to calculate molarity from normality. So like if you have 1N of HCl, so it's going to donate 1 proton per molecule. So your molarity is normality over N, it's 1. While in when you have 1N, so only like half of well, you'll see. 1N of H2SO4, you're going to donate 2 protons per molecule. So, since that's like the thing of interest that you have, so 1N over 2 is equal to zero point 0.5 molarity. Because remember, you only need half of that in order to produce 1 mole of hydrogen. So that makes sense that you it is basically saying that if you have like one equivalent of it, then you'll have zero point 0.5 molarity, because in order to produce 1 mole of it, you only need half of the total compound, so like zero point 0.5 moles essentially to produce one hydrogen. And that's what this equation is essentially saying. Um, just remember, tidbits, molarity, you care about the entire compound, so 1 mole. So it makes sense if you have more things of interest in a compound, it requires less solute to have the same effect. Representation of compounds. So we have the law of constant composition. So any compound has the same elements in an identical mass ratio. So, one water has like 1 oxygen and 2 hydrogen, atoms. It's essentially just saying like if you have a molecule, like you're not gonna have like any like just random thing out of wild card. Like you're not gonna have like 2 oxygens in water, for example. An empirical formula is the simplest whole number ratio. So if you're looking at benzene, which you'll often see depicted like this, it is the simplest ratio is CH. And the molecular formula is what gives the number of atoms per compound. So it's the massive number. So it's a C6H6 for benzene. Percent composition is how much of a particular element makes up the total compound. So you have the mass of the element over the molar mass, so like of the total compound, I should say, times 100. So specifically, if you're looking at oxygen in water, so I have approximately the molar mass of hydrogen is 1, and the molar mass of oxygen is 16. So 16 plus 1 is equal to 18. And 16 is the numerator because it's we're just looking specifically at oxygen, and there's only 1 oxygen in water. So 16 over 18 is around 89% oxygen. And remember, empirical formula and molecular formula might look a little different when you're looking at formula unit and formula weight. Remember, formula unit is pretty similar to your empirical formula, and molecular formula is pretty similar to over here for your formula weight. More or less the same thing. I think that's all I wanted to say over here. Let me just make sure. Yep, okay. Um, Types of chemical reactions. So this is just more or less like a jack of all trades chapter. So there's combination reactions, which hence the name kind of makes sense. So you're having A plus B, you combine it to make AB, or I it's like a new product C, I guess. So you're combining the reactants together. Decomposition, sort of like decomposing is breaking apart into smaller parts. So AB that I have or C is being transformed into A plus B. Now we're kind of getting into the more tidbits things, but combustion, just like sort of always think about like fire when you think of combustion. So it involves hydrocarbon, which is fuel or wood, and then oxidant or just oxygen from the air to always form water as and CO2. So that's why water is more or less a byproduct, like when you think of like burning wood, but CO2, that's like the stuff that will kill you eventually since it'll make your blood acidic. Um, Single displacement. So that's more or less like you're displacing a single thing from the reaction. You're not changing like into a whole new product. You're just like having the same things that were there. So our same elements are com things that make up the reaction. So C plus AB over here. And then I switched B with C to form AC plus B. And this is when only one switch occurs. So whenever you have an element by itself, it'll always have an oxidation state of 0. Um, and that is indicative of a redox reaction. So the single displacement is a redox reaction when one switch occurs. But a double displacement is when you essentially like they swap partners. So you're going from CD plus AB to AC plus BD. So two switches, not a redox reaction because you're keeping the same oxidation state. You're not having anything by itself. You're essentially just switching partners. Neutralization reactions are a type of double displacement reaction, so where acids and bases interact to produce a salt. Um, Also typically it'll produce water too. It's not always visible and often will have a metal and non-metal because that's like a lot of salts are, especially if you look at like the first column as well. That'll like be kind of indicative that it's a salt or nitrates. But last but not all salts involve metals and non-metals. That's what I'm saying. Like a large difference of electronegativity, ions. Um, Balancing chemical equations. So there are two rules that kind of must be followed. So it's a conservation of mass and conservation of charge. Makes sense. You can't just have like just add in another element or random mass from nowhere. It always has to be like from somewhere. And the charge too, like you can't just have like a random like charge in your products that came from nowhere. It has to be balanced as all things should be. Um, More or less, my little seesaw here. Can't just be like one way. Like you can't just like produce matter from nowhere. Or same thing with you can't just produce charge from nowhere. Stoichiometric coefficients are used to dictate how many moles are used for the atom or compound of interest. So over here, I have C3H8 plus O2 is going to be CO2 plus H2O, which, if you remember, you have a hydrocarbon, an oxidant, carbon dioxide, and water on the product side. That's a combustion reaction. So you're going to start with elements that appear only once on either side. So if I'm looking over here and I'm like, what only appears once? So it's not going to be oxygen. I'm going to save that for last. Um, but first thing I'm going to do is look at carbon. It could also be hydrogen too, since that only appears once on either side. So, but in this case, I just chose carbon because carbon is something that I just wanted to do. So over here, I see that there's three carbons. Over here, there's one carbon, so I'll add a coefficient of 3 in front of this molecule. So now I'll keep tally, and I have this little line always like right below the arrow to indicate that this is the reactant side. Uh, Reactants. And this is my product side. So now when I multiply this coefficient, it's kind of like imagine that there's like parentheses here, sort of. So it's like 3 CO2. So I'm multiplying it. Um, so three carbons, then oxygen, because it has a subscript of 2, I'm doing 3 times 2, which is 6. So now this is what I'm left with after that, adding that coefficient. And as you can see, it's still not balanced. So before moving on to oxygen, I'm going to go on to hydrogen because that also only appears once per side. And I notice over here, this has 8 hydrogens, and this only had, beforehand 2 hydrogens. So I'm gonna, in order to multiply to get to 8 hydrogens on this side, I'm going to put a coefficient of 4 here. So 4 times 2 is 8, and then 4 times 1 is 4. And over here, remember, I already had 6 oxygens, so now I have 10 oxygens. And over here, so you see I have 3 carbons, 8 hydrogens, that looks good. The last thing I need to work on though over here is that oxygen. And that'll be much easier to do because there's only 1 oxygen on this side compared to the 2 oxygens on this side that I would need to multiply. And also there's more as well. That's why you save it for last. It just makes it a lot easier to kind of have that checks and balances. So over here, in order to multiply and to get to 10 oxygens or moles of oxygen, I will have 5 times 2, and that'll give me to 10. And I just double check everything. So, 3 carbons, 3 carbons, 8 hydrogens, 8 hydrogens, 10 oxygens, 10 oxygens. Wow, looks great. So that's our full balanced equation. The more you do it, the more you pick up on this stuff. But I would recommend getting pretty quick just because sometimes you'll have to do it a lot. And don't, if you see a practice problem, don't just assume that it's already balanced for you. A lot of the times they'll try and trick you. Um, Also a couple other things that are important to keep in mind is that if you have a polyatomic ion, so like if you have like a sulfate or sulfite or like nitrate, nitrite, group it together. So like treat it as like one subunit. Like you'll see a subscript often, like, or sometimes you'll see subscript or like um etc. Like treat it as the same. So like if you were doing my little balancing stick here, it'd be SO4 2 minus on each side. I wouldn't add that oxygen to here. I would keep it independent. Also a fraction trick. So if you have a fraction like 3/2 of oxygen, so multiply both sides by the denominator, since that'll give you a whole number. So like if this was like 3/2, right? Not 3, I don't know, I did that. If you multiply each side by 2, so like this would be like, it's like multiply times 2, then multiply this side by 2. So it'd be 16, 20, and this would be 6. Obviously, it's not going to be since like this was already balanced, but 6. And then this will be 16. This will be 20. But notice because this is 3/2, that this is only 3. So, but it works. Yeah, I mean a good thing is just like always to have it on the just counting and separating like after each thing to see if it makes sense in your head. If you have like a really insane high number, then chances are something's a little funky. Um, yeah. The limiting reagent, sort of, now we're gonna get into like more of the stoichiometric problems. So a limiting reagent and excess reagents, those are two numbers that are not numbers, terms that you'll want to keep in mind. So limiting reagent is the reactant that is used up first in a reaction. So why you get the amount of product that you do. Whereas the excess reagent is a reactant that is left over but cannot be used because you don't have like two of reactants or the reactants that you need in order to produce a product. So before the reaction, notice I'm at A, um, moles of A, moles of B is equal to C, or the product. Whereas over here, I have my C, the product, but because A was the limiting reagent, it gets all used up, but not enough for B in order for it to get used up. So there's still going to be some excess, but it can't react with A, so it's just sitting there. But if you were to add more moles of A, then B would also get used up. So always consider the limiting slash excess reagent in moles. So don't do grams, do moles. And try and keep in mind the stoichiometry as well. So for an example, I have 27.9 grams of iron, which will react with 24.1 grams of sulfur to produce FeS, which is the limiting reagent, and how many grams of excess reagent are left. So over here, it's pretty simple. My balance equation, there's not any coefficients that I need to add. It's just a simple combination reaction. So I have iron plus sulfur is equal to FeS. So 27.9 grams of iron. I just looked up what is it on the periodic table. And remember, since similar mass, that's what is on the periodic table. So 1 mole. And then because these two are equivalent, there's 1 mole, the ratio is 1 mole to 1 mole. I could just sort of have it be like the full thing is just kind of like 30 over like 60-ish, which is around zero point 0.5 moles, whereas 24.1 grams of sulfur, 32.07 grams of sulfur is the molar mass of sulfur. And then again, that's a 1-to-1 ratio of moles of sulfur and moles of FeS, which was equivalent to 0.75 moles. So over here, my iron is going to be my limiting reagent, because think about it, it only produces like zero point 0.5 moles of iron. So like only like zero point 0.5 moles of iron are reacting to produce zero point 0.5 moles of FeS. So the maximum of 0.75 moles will not be reached, and there will be a 0.25 moles of excess. Because remember, zero point 0.5 moles are reacting, right? So that's like the capacity for it to react. So 0.75 minus zero point 0.5, so that's 0.25 moles that will not be touched of that sulfur. Um, After the reaction is completed. But if you want it in grams, you could just kind of do the same thing where you'll have the molar mass of 32.07 grams, but instead I'm flipping this. So like this got flipped because notice how grams is in the denominator here, but we want grams in the numerator here in moles in order for that to cancel out in the denominator. So it's 8 grams of sulfur. Woohoo. Yields, real quick. There's two different types of yields that y'all, or three, I should say, that you really need to pay attention to. So theoretical yield is if everything turns out perfectly, so no energy or human errors, which is impossible, unfortunately. I guess I never say never, but pretty much. It's what the reaction should lead to. So if it's the idealized product, that's why it's theoretical. Actual yield, so that's the amount of product that we actually have in a lab setting. So they'll make you calculate that a lot in Gen Chem. Some people can have like 300% yields, or they can have like, or I should say like percent yields, whereas other people will have like 5% yields, but we'll get into that. It's like if you have like way more than the theoretical yield. Um, for scent yield, as I was saying, that's kind of like the way to tell how well you performed a lab. So if you have too high or too little, it's both not good. It's like a sweet spot. It's like that 80 to 90 percent range. So typically it should be less than 100%, but sometimes you'll have more. I am guilty of having more sometimes. Um, where you'll have your actual over your theoretical yield, because technically your theoretical should be higher. If your actual, if you're adding more mass than the what is initially there, then that means that you have a contaminant. Not to say that you don't wouldn't necessarily have a contaminant anyways, if you had less, but that's like a clear indicator that it got contaminated, or there's just essentially it's something there that shouldn't be. Um, because you can't make nothing out of something out of nothing. Yeah. Um, Over here, if it'll let me scroll, maybe. Come on, OneNote. Some nomenclature for oxygen is you'll have ite, whereas you have less oxygen. So kind of think of it like the light version of drinks, like Bud Light or like one of like the alcoholic drinks, I guess you could say, or like Coke Light. I don't think there's Coke. I don't know, but Sprite Light, maybe I don't know. Eight is like more oxygen. Think of like the molecule eight, all of the oxygen nearby. Whereas hypo, remember like hypothermia, or like you have like less heat, or like anything with hypo kind of less. So it has the least amount of oxygen. And per has the most amount of oxygen. And then last thing I kind of want to talk about is electrolytes. So that are solutes that give solutions a charge, but they are not limited by the rigid lattice structure because they are in a liquid state instead of a solid state. So they're good conductors. So it allows those metals that have kind of like loose valence electrons. They're not really like super drawn to its nucleus, it's able to kind of have like expand and do its thing, be a good conductor. That's like important for electrochemistry, which is the last chapter of the Kaplan chemistry textbooks. That's kind of all I wanted to say about compounds and stoichiometry. Hopefully that was interesting. Yeah, once again, my name's Cha Cha.